Okay, so here we have a right triangle with sides A, B, and C and the angle theta. And you know that from basic trigonometry that sine theta is defined to be the opposite leg, or rather the leg opposite of the angle theta over the hypotenuse, B over C. Cosine of theta is adjacent or A over hypotenuse, which is C, and tangent is opposite over adjacent or B over A. And so if we have numbers, we could have, say, a 45-degree angle. And then that means that these two sides over here, the two legs, would be the same. So let's just call them, say, 1 and 1. Hypotenuse would be square root of 2 by the Pythagorean theorem. And so sine theta is 1 over root 2. Or you can rationalize it as root 2 over 2. Cosine theta is the same thing, which makes sense because we have an isosceles. Oops, should be a 2. We have an isosceles right triangle, and tangent would be equal to root 2 over root 2, which is 1, because the two legs, I should say, are the same. Now the problem is what happens when you have an obtuse angle, or even a right angle. When you have an angle that doesn't fit in a right triangle, what would its sine and cosine be? Well, what we end up doing is we extend the definition of sine and cosine a little bit. So here we have a set of axes. I'm not going to call them x and y. I'm going to call them u and v, just so we can refer to them, but without thinking of x and y, or like y is a function of x, because we're really just using this as a coordinate system. And so let's draw an angle. For example, this nice 60-degree angle. And if I draw this 60-degree angle, I can kind of draw this right triangle. And, well, I don't know how long these lines are, so I kind of have to start by giving one of them length. Let's just call this 2. Let's just say that's 2 units long. And, you know, the reason why I'm using 2 is because we have this 30, 60, 90 triangle, so this side would be 1 and this side would be root 3. And so we can go, okay, well, the sine of 60 degrees is opposite over hypotenuse with 3 over 2, and the cosine of 60 degrees is the adjacent over hypotenuse, or 1 over 2, which, you already know that. Nothing really new. But I want us to look at this point. If you look at that point, the coordinates there are, well, first the u coordinate, how far the point is away from the v-axis, or how far to the right is it from the origin. That would be 1 unit, and then you go 3 units up. So same thing with x and y, except I'm calling them u and v, just different letters. So notice that you can actually find the sine and cosine of the angle 60 degrees, not really by looking at the sides, but looking at the coordinates of the point. I mean, ultimately they're the same thing, right? Because you go 1 to the right, and so the length of the bottom leg is 1, and so the u coordinate is 1. But you can still use those coordinates as opposed to the sides if you didn't want to draw the sides, if you were just given the coordinates. So what we're going to do is we're going to kind of do the same thing, except with a bigger angle, with an obtuse angle. Say let's make it a little better. There we go. A 120-degree angle. And then I'll make this length 2 again. And then I'm going to drop this sort of vertical line down here. And so the question is, what are the coordinates of this point? Well, if you look at this triangle on the left, we have a 60-degree angle here. This is 60 degrees because the whole thing from left to right, or right to left if you will, is 180. It's a straight line. So 120 supplementary angle is 60 degrees. They add up to 180. Another way of thinking about it is, remember that 60 degrees is the reference angle of 120 degrees, because this angle here, 60 degrees, is how far this line is from the horizontal or the u-axis. Let me label my axes. And so 60 degrees, we can actually call that theta sub ref, theta reference, while 120 degrees is our actual theta. Okay, anyway, so we have the 60 degrees, we have this right triangle with a hypotenuse of 2, and so since it's 60, 30, 90, we can say this is 1 and this is root 3 again. And so the coordinates are going to be minus 1 and root 3. Still going up by root 3, but you're going to the left by 1. Now, if we go back up here, we go and say, oh, 60 degrees. Sine of 60 is root 3 over 2. That's sort of like the second coordinate, the height over hypotenuse, which is 2. And the cosine is the width, which is 1 over 2, because our angle is based on the horizontal. So width means adjacent and height means opposite. And so now, if we kind of go back here, well, what's the height? The height is root 3. It's the second coordinate, just like here. In fact, you notice that the coordinates are the same because we have the 60-degree angle up here and then the 60-degree reference angle in the second one. So we'll take a look at that relationship later. But the important thing is that over here on the top, we used root 3, the second coordinate, for the sine of 60 degrees. So what we're going to do is we're going to kind of do the same thing and say that, or rather, let's use a better word. We define the sine measure of 120 degrees to be this v coordinate, the second coordinate, root 3 divided by the hypotenuse, which is 2. And I can write this down as root 3 is the v coordinate. Yes, this can get confusing because u and v look very similar over the hypotenuse. And you'll see it as v over r. R kind of is like, why don't we call it h? Why do we call it r? Well, there is a reason. We'll look at it later. And similarly, instead of using the width 1 or the first coordinate 1 here, we use the width 1 or the first coordinate. Wait a second, that's negative 1. Well, remember that you can't have a negative width in geometry, but in coordinate geometry, this minus 1 I just put a little box around, it's not really the width of this horizontal line here. It's really which direction and how far you go to get to that point horizontally. So we can still have negative numbers. It still makes sense. We're not doing negative lengths. And cosine of 120, we'll define that to be u over hypotenuse, the first coordinate, so negative 1 over 2, or u over r if we want to use the letter r as short for hypotenuse. It's a little weird, right? Because cosine you think of as adjacent over hypotenuse, but now we're saying it's negative something over 2. The hypotenuse part is familiar, but the adjacent is still minus 1. But you look at this picture and you go, well, isn't adjacent 1? But remember that when we say the adjacent side is 1 or whatever, we're looking at this 60-degree angle. So for this angle, the adjacent side is 1. But this angle, 120, the one I'm making purple here, is not the 60-degree angle. It just happens that we use that reference angle, that 60-degree angle, to help us find the sides of the triangle and get the coordinates of the point minus 1 root 3. So in some sense, even though it's very similar to this example, the answers are kind of the same, except with a negative sign. Over here, we are doing a very different problem. 120 degrees, 60 degrees, not the same thing. 2 is not equal to 1. If it was, we'd have issues. So let's kind of summarize this. To find the sine of any angle theta, what we're going to do is redraw the angle in standard position, so like what we did with the 120-degree angle, and then we calculate v over r. And for the cosine, we calculate u over r. Now this is kind of super confusing because sine usually comes first because we say sine and cosine, but sine is the second coordinate over r, and cosine is the first coordinate over r. And it gets really confusing, but it's unfortunately the way that things are situated, so we'll just have to kind of get used to it and hopefully not confuse ourselves too much. Oh, since we're at it, may as well write down tangent. Tangent is opposite over adjacent, and since v takes the place of the second coordinate takes place of our opposite, and the first coordinate takes place of adjacent, we go v over u. And remember that r is given by the square root of u squared plus v squared, because of the Pythagorean theorem, r squared is u squared plus v squared. Right? No matter where you are, no matter where the angle is, which quadrant you're in, you still have this square plus this square equals this square. And over here you have, well, I guess minus 1 square, which is the same thing as 1 square, plus root 3 square equals 2 square. So the minus signs, when you're in a different quadrant, doesn't really affect the Pythagorean theorem, because when you square a minus sign, it goes away. So these are the important relationships in finding the cosines, the sine, cosine, let's do it in the right order, tangent of any angle from 0 to 360 degrees. So let's look at an example. Let's do one of these things. Start with something simple. Say, I don't know, oops, that's a wobbly line. 225 degrees. There we go. And the first thing we really need to do is to, figure out where this point is. Now notice that we kind of back in the first two examples, we kind of just said, oh, that point is 2 units away from the origin, and I kind of didn't say why 2 is special. Although I did, I said it's easy, it makes the numbers easy, but that's not really the best reason of doing something, to make the numbers look pretty. So the question really is, how long do I make this arrow that I just drew? And the answer is, remember, it doesn't actually matter, because sine, cosine, and tangent are ratios. Back when you did regular basic trigonometry with right triangles, it didn't matter how big the triangle you drew, as long as you had the correct angles, I should say, not right angles. As long as you have the correct angles, the ratios will end up being the same. Sine, cosine, and tangent are measures related to angles, not lengths. The division really kind of cancels out any factor. So what we usually do is we actually call this 1, because we really don't, or sometimes we just don't have like really good numbers. So we're just gonna make the hypotenuse 1, and that will make our lives easier, because we kind of standardize. Now the question is, what's the reference angle of 225 degrees? So if theta is 225, well, 225, it's in the third quadrant, so to find kind of this angle, we subtract 180 degrees, and that gives us 45 degrees, and that's theta ref. So this over here is 45 degrees, which means that we have a 45, 45, 90 isosceles right triangle down on the bottom left. And since this is isosceles, we can say that this point really has the same coordinates. It's going to be minus something to the left, and then minus something down. The two coordinates are going to be both negative and the same. And since we don't know what it is, let's just call it A, right? And we're going to figure out what A is using the Pythagorean theorem. Minus A, I don't really need a minus sign because I'm squaring it. Square plus minus A squared equals 1 square. That means A squared plus A squared, or 2A squared, equals 1. And so A squared equals 1/2, A equals 1 over root 2, or I actually should have wrote this first, root 1/2. And I guess you can do root 2 over 2 if you wanted to rationalize it. And hey, look at that. Looks familiar because it's a 40. We have a reference angle of 45 degrees. In fact, back in the original example right here, root 2 over 2 and root 2 over 2 were the sine and cosines of this angle, 45 degrees. But now if you come back here, remember that we're not dealing with 45 degrees. We're dealing with 225 degrees. So let me redraw the diagram down here where there's like a little more room. All right, let me give myself a little more room. So, nice big diagram. Here's 225 degrees. And a reference angle of 45. I won't draw that in because the reason why we really needed a reference angle is to find what this length and this length were. And what we got was that they were both root 2 over 2. But remember that even though these are lengths, but the coordinate of this point, because we're going left and then down, is minus root 2 over 2 and minus root 2 over 2. And so let's use our formulas, or rather our definitions. Sine of 225 degrees equals v, the second coordinate, over the hypotenuse, which is 1. So that would be just minus root 2 over 2 all over 1 minus root 2 over 2. And the cosine of 225 degrees is minus root 2 over 2, the first coordinate. You really can't mess them up in this one because they're the same. That's pretty cool. Over 1, which is equal to, whoopsies, there we go, just minus root 2 over 2. So the sine and cosine of these of 225s, just like the ones of 45 degrees, it's reference angle, but they're all both negative because we're now in the third quadrant and the coordinates are both negative. One other cool thing, I don't know if you just noticed, about using 1 as the hypotenuse is that you're dividing by 1 here. Right? Remember our formula says divide by the hypotenuse, divide by r? Well, if r is 1, you don't really do anything, which is pretty awesome because, if you can save a step by not doing the division, you do less work and it makes everything quicker. Okay, let's do one more example. One more example. So this time, instead of just putting in an angle measure and finding the coordinates, we're going to start with the coordinates. So this is going to be, this is in the fourth quadrant, so the first coordinate, u coordinate, is going to be positive. Let me label my axes and not be lazy. There we go. Okay, and draw little arrows. So this thing over here is going to have a u coordinate of 20 and a v coordinate of negative 12. And this is our angle, theta, and this measure, or this angle, is the reference angle, theta ref. We don't really need the reference angle this time because we already have the coordinates. So, I guess I should put down a problem first, right? So the question is, what are sine theta and cosine theta? All right, so sine theta is the v coordinate over the hypotenuse, or v over r. V is the second coordinate because v comes after u. That's minus 12. But wait, what's the hypotenuse? Oh crap, we don't have the hypotenuse. We need to find it. And remember that the hypotenuse is given by r squared equals 20 squared plus minus 12 squared. R squared equals u squared plus v squared. So r squared equals 400 plus 144. That means r is square root of 544. And so sine theta is equal to the v coordinate, which is minus 12, over root 544. And cosine theta equals the u coordinate, 20, over root 544. So when you're actually given the coordinates, finding the sine and cosine of an angle is really super easy. The problem is that usually you go the other way around. You kind of, or rather, I shouldn't say you go the other way around. I should say you you don't have the coordinates and you have to find them using reference angles like I did up here with this example, right? With 225 degrees. I'm only given 225, so I have to draw it, find a reference angle, find the coordinates of the point that the angle points to, blah blah blah, and then do all that stuff. But if you have coordinates, it's wonderful. Just need to figure out the hypotenuse, or if you're missing one coordinate or whatever, figure it out using the Pythagorean theorem, which you've known well for a very long time probably. And then you plug everything into the definitions. Sine is v over r, cosine is u over r. And poof, you're done. Sine and cosine.